Cool. So we want to calculate residues. So we want to be able to calculate residues. Now, in the case when we have a simple pole, it's rather easy. So suppose F has a simple pole at Z0. Then what does that mean? That means Z is equal to a to the minus 1, Z minus Z0. It's the minus 1 plus some holomorphic function like this. Yeah? That's exactly what simple pole is. The order of the pole is 1, so therefore that's the only term in the principal part. Then, if we just look at this, let's take the limit as Z goes to Z0 of Z minus Z0 times F of Z. What happens to this? This is the limit as Z goes to Z0 of, just multiply this thing through, of just a to the minus 1 plus Z minus Z0 h of Z. H is a perfectly nice holomorphic function. It has a limit as Z goes to Z0. So this part here will just vanish. So that's just equal to just a to the minus 1, like this. Yeah? So this thing gives us the residue in the case we have a simple pole. In a more general case, we have to work a bit harder. So theorem. Suppose F has a pole of order n at Z0. Then we're going to get the formula by taking Z minus Z0 to the n and then multiplying this by a function like this. And then we want to differentiate this n minus 1 times. And when we do that, we're going to have a bunch of factorial expressions which we want to divide through. So we're going to divide by n minus 1 factorial. And that thing will be the residue of our function at f of Z0. Oh. So Stein's notation is to put the Z0 here. I'm a bit tempted to do this because I feel like the Z0 is pretty small for you to see if I put it as a subscript. So maybe I'm going to write this. Maybe I'm going to write it like this. Do you prefer it like this with this notation, or are you happy with this? Give me a thumbs up if you prefer this notation. All right. Just two of you. So it seems you don't mind. All right, so we'll continue with the Stein notation. All right, so this is what we have. So why is this true? This is a calculation. So if we have that it has a pole of order m, what does that mean? That means f of z is of this form, the sum from k equals 1 up to n, a to the minus k, z minus z0 to the minus k, and then plus the holomorphic part that we don't have to worry about. So when we multiply this thing by z minus z0 to the m, to the n, I should say, what happens? Then we get just this thing, k equals 1 to n, a to the minus k, z minus z0 to the n minus k, and then this part here, which is harmless for us, h of z. Yeah, let's write out some of these terms just to make this clearer for us. What do we have? So we have a to the minus n, and then we're going to have z minus z0 now let's start it from a to the minus 1. So we have a to the minus 1, and then we have z minus z0 n to the minus 1, and then we have a to the minus 2, z minus z0 n to the minus 2, and then so on. When we have k is n minus 1, we have a to the n minus 1, and then z minus z0 to the n minus 1, so this is just to the power 1, and then the final thing is a to the minus n, and that's just going to be n minus n, so that's just 1, n to the minus n, and then this stuff here, which is z0 to the n h to the z. Yeah? Just writing out what this is. So let's think what happens when we differentiate n minus 1 times. So if we differentiate this thing n minus 1 times, right, then every time we differentiate it, we're going to put down the power, put it in front, right? And then if we differentiate n minus n times, what happens to it in the end? What does it turn into? Let me put it somewhere. So we're going to differentiate this thing, z minus z0 to the n minus 1. What is it going to turn into? Yeah, just n minus 1 factorial. Yeah? Because every time we differentiate it, we put this number down in front, we lower the power. Yeah? We do this n minus 1 times, it's going to be n minus 1 minus n minus 1, which would be 0. Yeah? So we end up with this thing. Are you all with me here? Give me a thumbs up if you are with me. Okay, cool. All right, what happens when we differentiate this thing n minus 1 times? We get 0. Yeah, we get 0. What happens if we differentiate the next term here? 0 again, right? Differentiate this thing n minus 1 times. 0 again. This thing, of course, 0 is a constant, right? So then we just have to think about what happens when we differentiate this thing n minus 1 times. Yeah? So let me try and put it on the bottom here. So if we differentiate d n minus 1, say that again. If we differentiate n minus 1 times this expression here, in order for our theorem to be true, this thing can't be a problem when we take the limit as z goes to z0. I hope I did put that. I didn't put that. Sorry. Didn't put the key thing. So this thing is differentiated as we take the limit as z goes to z0. So it's the analog of this result here. It's the higher dimensional analog of this result here. So this thing right here, if it's true, then we should not have this guy playing a role, because we've seen that the only thing that is remaining when we differentiate all of these guys is just the thing that we want, the a minus 1 coefficient and then n factorial. Yeah? You see what I mean? Yeah? So in order for this theorem to be true, what we would like to have is that this guy here doesn't mess things up for us. Yeah? Because if we knew this thing was 0, then our theorem would be true, because that's what we've just seen. Yeah? So backward engineering what we want, we'd like this thing not to mess things up for us. And I claim that it is the case, that it will not mess things up for us. And it just follows from looking at the expression. So look at this expression. We don't need to understand too much about this, except that when we take the limit as z goes to z0, that this thing will go to 0. That's all we need for this thing. Huh? We need this guy to die quietly. So So what about this guy allows us to conclude it dies quietly when we take z goes to z0? Perfect. Perfect. Yeah. Yeah. So if we use the product rule over and over again, so let's just differentiate once. We hit this guy, we'll reduce the power by 1, leave that guy alone, then leave that guy alone and hit this guy. Yeah. And that expression still has a factor of z minus z0 to the n minus 1. Yeah. Yeah. So we would now be differentiating z n minus 2 times an expression with z minus z0 to the n minus 1. Yeah? And then we just keep doing that. Yeah? We just keep doing that. And every time we do it, we find that we still have a power left as we still, let me say that better. Right now we're differentiating n minus 1 n times, and we have a factor of z minus z0 to the n. And every time we do a differentiation, we're still going to be differentiating a certain number of times, but we're going to have a factor of z minus z0 to that number of times plus 1. Yeah? That's what will happen every single time. So that when we go all the way through this entire procedure and differentiate all n minus 1 times, we're still going to have a factor of z minus z0 to the power 1. In all of the expressions, in all the terms. It'll spread out like a massive, massive, messy thing, but every single term will have at least the power of z minus z0 to the power 1 in front of it. Huh? So that when we take the limit as z goes to z0, this entire guy will just vanish. No? This entire guy. So just summarizing that, this expression will be of the form z minus z0 plus some other thing. Let's call it g of z. For some g, yeah? Well, this is a nice holomorphic function, whatever. We don't care about it, yeah? So, putting it up here, so the limit as z goes to z0 of n minus 1 derivatives of our expression here. It's really badly written. Of z minus z0 to the n times h of z. This is, sorry for this terrible board management. Is equal to 0. Yeah, that's what we have. That's what we have. Yeah? So sure enough, this guy dies quietly. It isn't a problem for us. When we take the limit as z goes to z0 of this entire expression, yeah, all we're going to get out is just a to the minus 1, because we know that the only survivor of the differentiation of this part is just a to the minus 1 times n minus 1 factorial. Yeah? Yeah? And everything else, everything else just vanishes. And then when we take the limit as z goes to z0, this guy just is not a problem either. Or this guy differentiated n minus 1 times is not a problem either. By this, no? No? So then all we get in the end is just n minus 1 factorial times a to the minus 1. So we divide by n minus 1 factorial and we get exactly the residue. Okay, cool. All right, so this is a complicated looking formula. And the way to do this is not to memorize the formula. Memorization is strictly forbidden. Some of you, probably all of you, have very good memories. Some people have outstanding memories, and they go very far being able to recapture the form of formulae, and they get all the way to graduate level. But that is not what you want to do. Switch off your memorization abilities in this course, or in any course actually. What you want to do is to backwards engineer this thing. You want to backwards engineer it from what you know about how it works. How does it work? We have this thing here. We want to extract out the n-1 coefficient. So the natural thing to do is to multiply by z to the z minus z0 to the n. Because then that produces something like this, and then we differentiate n-1 times. We're going to kill a whole bunch of stuff. In fact, we kill everything when we take the limit as z goes to z0. So do not memorize this. Do not memorize this. The way to know this is to take a piece of paper and try and work out the formula for yourself, just from the representation, just from some vague memory. Okay, this is the only thing you're allowed to remember. The only thing you're allowed to remember is that you're going to take the expansion for f, and you're going to multiply it by z minus z0 to the n, and then you're going to do some differentiation. That's all you're allowed to remember. So when you revise for this topic, just take a piece of paper, and with the fact that you have the expansion, which is easy, you should know the expansion at this point, and the memory that you're going to multiply by z minus z0 to the n, and you're going to do some differentiation, work out the formula. Work out the formula. And once you've worked out the formula a couple of times, you will not have any problem with the formula, because it will seem natural to you. But just watching me, it might seem natural, but it won't seem nearly as natural as it will be if you actually work it out yourself. And this is what you have to do. This is, as I said before, that since you're applying to enter research, you're going to have to learn mathematics at a deeper level than you've learned previously. You're going to have to absorb the machinery, the techniques of your research field in a very fundamental way. Not enough to know the statements, not enough to have verified the proof and believe it's true. You're going to have to just have the essence of the theorem inside you, and just be able to recapture the main techniques to prove it. You're going to have to learn things at that level to make any real progress in anything, in any area of research.